Hello and welcome to the section Decorators and Non-Type Annotations. In this section, we're going to talk about a couple of things that I most like about Python, those being metaprogramming and metadata, specifically. So now, let's look at the first video, Decorators on Functions and Classes. In this video, we'll start off by looking at decorators and how to apply them to functions, methods, and classes. First though, there's a fundamental idea we need to get a handle on. When we refer to a function or a class as being first class, it means that there's an object present in the program which is that function or class. And we can store that object in a variable, assign it to a different variable, pass it as a function, parameter, or return value, and do anything else that we could do with any other data value. It's like a ball sitting in our backyard, which we can touch, pick up, move around, and just generally use and interact with however we like. In some programming languages, including very common ones such as C++, functions and especially classes do not have that property. They exist, but we can't just treat them like any other data value. We can see them, but we can't touch them. They're like the moon. We're talking about this because decorators use functions or classes as their input and output data values, which is only possible if functions and classes are first class, and only makes sense if we understand the functions and classes are first class. Here we see the code for two functions, one called printer and one called hello. The printer function is very simple. It accepts one parameter, prints it out on the screen, and then returns it. Simple though it is, this function is a valid decorator because it will work fine when its single parameter is a function. It also happens to be a valid class decorator because, again, it will work fine if its single parameter is a class. After that is an even simpler function definition for a function called hello. This is a function requiring 3 parameters and returning none. There's nothing special here, except the line before the def says @printer. That syntax, an @ symbol followed by an expression that produces a valid decorator, is how decorators are applied to functions or classes. Here, we are telling Python that the hello function is decorated by the printer function. So, we ran our program, and it printed out a representation of a function. Why? All we have here is 2 function definitions, after all. Why did our program do anything? It's because that's what decoration actually means. When a function is decorated, the decorator function is called with the decorated function as its parameter when the decorated function is defined. It's equivalent to doing this. When we look at this program, it's not at all surprising that we see a printout when we run it. We just have to remember that this is what it means when we apply the decorator using the @ symbol, and everything makes sense. Notice that not only is the decorated function used as the parameter for the decorator, the decorator's return value replaces the decorated function. That's why it's important that our printer function returns the same value that was passed to it as a parameter. If it returns something else, an integer, a string, or none, then that would be what the name hello referred to afterwards. That's a feature because sometimes it's very useful to have our decorators replace the thing they're decorating with a different value. But when we don't want to replace the original value, function or class, it's important to remember to return it. If we forget to have the return statement at all, Python will assume we wanted to return none, and that's almost never right for a decorator. Speaking of replacing the decorated function, there's something particularly useful we can do with that called wrapping the function. Wrapping a function means that we replace the function with a different function which calls the original function. But of course the wrapper function can do more than just call the wrapped function. It's also able to run its own code before the wrapped function, or after it, or both. The memoize function here is a decorator which wraps the function it decorates inside of a wrapper which keeps track of the mapping of function parameters to return values, and skips calling the wrapped function if it already knows what it's going to return. This isn't always a useful thing to do, particularly in cases where computing the return value is not the main reason for calling the function, or when the return value is not entirely determined by the parameters. But in cases where it is useful, it's nice to be able to package that pattern in a decorator, and simply decorate any function that would benefit from it, thus replacing those functions with wrapped versions. We can see that here, where all the memoization infrastructure would have severely detracted from the readability of the Fibonacci function. Instead, we've separated it out and made it reusable, which is certainly a win. The actual structure of this decorator is interesting. First of all, we've defined the memos dictionary here within the scope of the decorator function. Python is a lexically scoped language, so this dictionary is available to the wrapper function, but essentially invisible to the rest of the program. We're also defining the wrapper function right here, inside the decorator function. That gives it access to the memo dictionary and to the function parameter that was passed to the wrapper, If we decorated several different functions with memo-eyes, each wrapped function would have its own memos dictionary and wrapper function, even though the wrapper functions would all be the same apart from the values of the variables they access. The wrapper function uses a bit of special Python syntax to indicate that it can accept any number of positional parameters and any number of keyword parameters. That's what the single asterisk and double asterisk mean, respectively. Doing that is fine, because no matter what parameters are passed to it, all it does is use them to generate a dictionary key, and possibly pass them on to the wrapped function. If the parameters are incorrect, the wrapped function can raise an exception. That's a common pattern for wrapper functions, since it's usually the wrapped function that actually determines what the parameters should be. As we noticed before, it's important for the decorator to return a meaningful value. Before, that was simply the decorated function, resulting in that function being left in place. This time, we're returning the wrapper function, which means the wrapper will replace the decorated function, as far as the rest of the code is concerned. When we run the program, it prints out the first 10 Fibonacci numbers, as expected. That really only proves that the decorator and wrapper work the way I said they do, but it's nice to see. There's one problem with wrapper functions, and that is that they obscure the wrapped function. The result is that Python's built-in documentation system, along with IDEs and other tools that rely on Python's introspection features, don't really work, or at least they don't provide useful information. Fortunately, there's an easy fix. There's a decorator in the standard library called functools.wraps. If we apply that decorator to our wrapper, and yes, that means that we're decorating a wrapper function that we're defining inside of a decorator, the problem goes away. Now, when we use introspection on the wrapper function, we get back information relating to the original wrapped function. That makes the wrapper transparent to help tools, IDEs, and so on, with the result that we can generally get better and more useful documentation from them. There's something else here that we'll want to talk about. This decorator accepts a parameter. How does that work? Remember that we apply a decorator by writing an @ symbol followed by an expression that evaluates to a decorator. Previously, that expression was simply the variable name of the decorator function we wanted to use. This time, it's a function that has a decorator as its return value. Here's the basic pattern for doing something like that. Our clamp function takes parameters and returns a decorator. The decorator accepts one parameter, the function it's being applied to, and returns a wrapper. The wrapper in turn accepts any combination of parameters, passes them on to the wrapped function, and does its processing before returning a value. So now we have three functions nested inside each other, each handling a different part of the process. The clamp function gets run first, as the expression that produces a decorator. Then the deco function gets run, as the actual decorator. All that happens once when the program is loaded, and never happens again. However, the wrapper function gets called each time the wrapped function is to be called, and is responsible for actually calling that function, along with whatever else it needs to do. We can apply more than one decorator to the same function, but when we do, order matters, or at least it can. The rule is that the decorator which is closest to the function definition runs first, then the next closest, and so on. Put another way, they run from bottom to the top of the list. If the decorators do things that are completely unrelated, that probably doesn't matter. But in cases like this one, where both decorators operate on the return value, they're going to interact, and the order they run in matters. Here, we're saying that the return value should be clamped and then squared, producing a value somewhere in the range between 100 and 2,500. Now we're telling Python that the return value should be squared and then clamped, producing a value in the range between 10 and 50, with a high probability of being 50. That's a real difference from before. Functions aren't the only thing that can be used as a decorator, though that are particularly common. Any Python callable object can do the trick. Particularly interesting are classes. A class is callable, and the call operation creates a new object and runs the class constructor to set it up. So if we have a class with a constructor that accepts a function or a different class as its only parameter, we can use that class as a decorator, and the original function or class will be replaced with an instance of the decorator class. That gives us a different way to structure our decorators and wrappers. This is the same memoization pattern we saw before, but this time implemented as a class instead of as a function. This is almost the drop-in replacement for the decorator we saw before, but there are a few differences. First, structuring it as a class might make it easier or harder for particular programmers to read. People have their different ways of understanding things, and different approaches are more clear to different people. Second, the memo and func attributes of the class instance are accessible to the rest of the program, rather than being confined to the lexical scope of the decorator. This could be useful or problematic depending on the situation. Third, we can't use the functools.wraps decorator to make our class instance appear to be a wrapped function. Class instances are just too different from functions for that to work. Instead, we'll need to make sure that our class instances provide useful information when introspected. Finally, a note. Our memoize class is callable, as all classes are, but instances of the memoize class are also callable because they implement the underbar call underbar magic method, allowing them to emulate the function call syntax. This is what allows our memoize class to act as a decorator, and instances of that class to act as wrappers. Decorators can apply to classes as well as functions with the same rules. The decorator has to accept a class as its single parameter, and whatever the decorator returns will replace the class. That's what's going on here. The data class decorator, which is part of the Python standard library starting with Python 3.7, is taking our animal class as its parameter, and replacing it with a class that has a constructor accepting parameters for the attributes we defined in animal, and storing them as instance attributes, a nice printable representation, a useful comparison operator, and more. In essence, the data class decorator is creating a new semantic meaning for the class it decorates. The possibilities opened up by decorators are endless, but we'll leave off here for now. Decorators will also feature in the next video,